Hi, my name is Christian Davison, and this is my Physics 2212 Lab 1 report on charged tapes. So, the purpose of this lab is to observe the interactions between pieces of tape and determine the amount of overall charge, as well as the excess amount of excess charge on pieces of tape. The materials include clear tape, a ruler, flat surface, and object to support tape, and the GlowScript software to computationally model the tape and interacting forces. The result was that the charge on each tape was determined to be 1.167 times 10 to the negative 8 coulombs, and the number of electrons lost by each tape was 7.294 times 10 to the 10 electrons. The gravitational force between the floating tape was 1.962 times 10 to the negative 3 newtons, and the electric force is equal to the magnitude of the gravitational force, so 1.962 times 10 to the negative 3 newtons. The fundamental principles used were Coulomb's law, which describes the force of attraction or repulsion between two charges, where K is 9 times 10 to the 9 times the first charge of the first charge times the second charge, and then the radius between the two charges squared. And Newton's second law, which is the sum of all forces external to the system acting on a system, which is F is equal to ma, and then the force due to gravity, which is just F is equal to mass times acceleration due to gravity, so negative 9.81 meters per second squared. The initial conditions were that the tape mass was 2 times 10 to the negative 4 kilograms, the tape length was 0.02 meters, and the tape's area was 0.004 meters squared, and we found this by multiplying the length times the width. The area of an atom was found to be 1 times 10 to the negative 20 meters squared, and the amount of atoms on a tape was found by dividing the tape area divided by the area of an atom, which was found to be 4 times 10 to the 17 atoms. So as we can see in the observed model, with no additional tape added, that the gist tape is at rest, but once the charged tape is put beside the resting tape, we can see that the resting tape rises by 0.025 meters. And we found the charge of the tape by rubbing a pencil on one of our lab mates' hair, so excess electrons are now coming onto the pencil, so the pencil is now negatively charged, and we found that the tape was moving towards the negatively charged pencil, and opposite charges attract, so this must mean that the tape is positively charged. So to calculate the excess electrons, we know that the gravitational force is equal in magnitude to the electrical force, and the gravitational force is found to be 1.962 times 10 to the negative 3 newtons, and we found this by multiplying the mass of the tape by the acceleration due to gravity to get that number. And then we rearrange the electric force formula, where K times Q, the charge is squared divided by R squared is equal to Fe. We arranged this to solve for Q, and we found that the charge was found to be 1.167 times 10 to the negative 8 coulombs. And to find the number of electrons lost, we took the charge of the tape and divided it by the charge of the electrons, and we found that to be 7.294 times 10 to the 10 electrons lost. And the ratio of atoms to electrons is the number of atoms divided by the number of electrons lost, which we found to be 5.48 times 10 to the 6th. And as we can see in the computational model, where we have K is equal to 9 times 10 to the 9, the charge of a proton is 1.6 times 10 to the 19. Charge of electron is the exact same but negative. And we can see that for the tape A, which is denoted by the blue ball, we can see that the force of gravity is pointing downwards, which is pointing down because gravity always points down. And as we can see that the electrical force is pointing in the opposite direction of gravity. And we can see this because they both cancel out, meaning that they're the exact same magnitude. And as we can see that in the computational model, and that the charge of each tape was 1.167 times 10 to the negative 8 coulombs, which is the exact same as in the observed model. And we also see that the number of electrons lost to the tape is 7.29 times 10 to the 10 electrons, which is exactly the same as the observed model, indicating that this experiment works in both computationally and in observed scenarios. Some possible errors include that the tape is not a point charge, and that a charge can peel off tape due to human contact. As no humans, our bodies are neutral systems, so us coming in contact with tape could cancel out a charge. And also the assumptions for the exercise is that air resistance is negligible. So what if the electrons had positive charge and protons had negative charge? What would change about the observations you made with tapes and other charged objects? There would still be a repulsive force between the tapes. The only difference is that they're both negatively charged instead of positive. And then when it comes to the determining the charge of the tape, the only real difference was that since we used a pencil to rub off electrons, instead of the tapes attracting the hair, the pencil and the tape, they would be repelling each other. Because like as I mentioned earlier, like charges repel. Why is it important to handle the charge of the tapes as little as possible? What happens when the charged tape comes in contact with your hands or other objects? As mentioned before, our bodies and other objects can act as neutral objects that neutralize the charge on tapes upon contact. This means we could no longer observe the desired electrical effects that require charged objects. And thank you.